Hello, this is my sixth lecture on real analysis for SEM 3 honors and GE students. I am Ms. Ranjana Dutta from the Department of Mathematics, the Graduate School College for Women. Today we will going to study definition of derivative. Let f(x) be a function defined on the open interval I, written as open interval AB, and let C be a point in I. Then the limit x tends to C fx minus fc divided by x minus c, or equivalently we can write limit h tends to 0 fc plus h minus fc by h exist is said to have a derivative at x equal to c. If it exists, then it is called the derivative at x equal to c and is denoted by f dash c. So f dash c can be written as limit h tends to 0 fc plus h minus fc by h. Now, limit h tends to c plus 0 fx minus fc divided by x minus c, and limit x tends to c minus 0 fx minus fc divided by x fc is known as the left hand limit and the right hand limit of this. Now 2 and 3 respond the right hand limit and the left hand limit of fx minus fc divided by x minus c when x tends to c. Therefore 2 and 3 may be conveniently denoted by R, that means right f dash c and left L f dash c respectively. The symbol R, F dash C and LF dash C are used to mean the right hand limit and the right hand derivative and the left hand derivative at x equal to C. The function fx is said to be differentiable at x equal to c if the right hand derivative and the left hand derivative both exist and equal. See, both exist. That is, right hand derivative should exist, the left hand derivative should exist, and the right hand derivative should be equal to the left of derivative. Now, derivation on the closed interval AB. When fx is defined on the open interval AB, fx is said to be derivable in the open interval AB. If it is derivable in the every point in the open interval AB. In such a case, we know that the f dash c, where c is any number between a and b, is defined by the limit h tends to 0 fc plus h minus fc by h. On the other hand, fx is defined as the closed interval AB, then fx is said to be derivable in closed interval AB if f dash c exists for every value of a belongs to open interval AB. eh, For every such value, AB belongs to C, and right hand limit exists and the left hand limit exists. Thus, if fx is derivable on the open interval and it is also at the end point, see here, it is derivable in the open interval and it is also derivable on the end points, that is a and b, then we say that the it is derivable on the closed interval AB. Now the geometrical meaning of the derivative. Let AP be the curve and P be any point in this curve, and the P be any point so that OM is equal to C, and Q be another point very close to P, and ON is equal to C plus H. Then PM is equal to FC and QN is equal to FC plus H. From P, draw a perpendicular PR on QN so that PR is equal to H and QR is equal to FC plus H minus FC. Then after that we know tan theta is equal to QR by PR is equal to FC plus H minus FC by H, which is the formula for derivation as limit h tends to 0. Let us let the tangent P and Q on the x-axis t such that ptx is equal to phi. Let the tangent at P meet the x-axis at t so that ptx is equal to psi. Now let the point Q moves along the curve to conclude with the point P so that as Q tends to P, that is as H tends to 0, then the chord QP approaches through to the tangent at PT, and then we can write theta tends to psi, tan theta is equal to limit h tends to 0 fc plus h minus fc by h, and tan psi is can be written as equal to f dash c. Thus f dash c is the tangent of the angle which the tangent line to the curve y equal to fx at the point P makes with the x-axis. Now see some example. A function theorem, a function defined on the closed interval AB possesses a limit derivative at the point of the interval from then fx is also continuous at that point. Let fx have a finite derivative f dash c at the point x equal to c, where c lies between the closed interval a and b. Then limit h tends to 0 fc plus h minus fc by h is equal to f dash c. Now we can observe that fc plus h minus fc can be written as multiplying and dividing. We can write it as fc plus h minus fc by h into h. Now fc plus h minus fc can be written as limit h tends to 0 fc plus h minus fc hh, and which on putting the limit which gives us 0. So f dash c is finite, hence we have fc plus h is equal to fc as h tends to 0, which implies that fx is continuous at x equal to c, where c belongs to closed interval ab. Now, take an example. Fx is equal to x, where x lies between 0 and half, and is equal to 1 minus x when x is greater than half and less than 1. Now we will find whether it is derivable at the point x equal to half or not. To, uh, to continuity and derivability both. Now, x equal to half. So f half minus 0 as calculated is equal to half. F half plus 0, that is right hand limit, that is equal to half, and f half equal to half. So right, since the right hand limit is equal to the left hand limit is equal to half, then the function is continuous at x equal to half. Now, to show the derivability, we put the formula, that is f dash half can be written as left hand side, that is written as you show on your screen, and it is the left hand limit is 1, and similarly the right hand limit is equal to minus 1. Since the left hand limit is not equal to the right hand limit, hence f dash half does not exist. Hence we can see that though it is the function is continuous at x equal to half, but it is not derivable at x equal to half. Now, take another function, another example. Fx is equal to plus root x when x is greater than or equal to 0, and equal to minus root x when x is less than equal to half. Left hand f dash x can be written as limit x tends to 0, f0 minus h minus f0 minus h. Since it is less than 0, then we take the function as minus root x, and after putting the value, we get it is equal to plus infinity. And right hand side fx 0 plus h minus f0 by h, where we put the function is equal to root x, and here putting the values in h as h tends to 0, we get it is plus infinity. Since the left hand limit is equal to the right hand, so f dash 0 is infinite, hence it is derivable. Next, to show the continuity, we check it is at f left hand limit and right hand limit and the central limit, and in all the cases the values comes out to be 0. Hence the fx is continuous at x equal to 0, hence proved. Students, I have given some example. Please try them at home today, this much only. Thank you.